second assignment is about national income model. We have two equations. First is y equals c plus I plus g, and the next equation is c equals c plus b bracket y minus t bracket. This equation is endogenous variable. Each income and consumption function has a continuous partial derivative. It's followed that each f1 and f2 has continuous partial derivative with respect to the variable. Thus, the first condition is satisfied. Since the Jacobian determinant for the endogenous variable is non-zero, no matter where is evaluated, Jacob is non-zero. The second condition is satisfied. Like this equation, Jacob will get 1 minus 1 minus b and 1. So the answer is 1 minus b. So the answer will non-zero. Therefore, there exists implicit function for f1 equals 0 and f2 is equal 0 at the equilibrium point. Thus, the implicit function at the equilibrium point can be written like this equation. Y equal f1 bracket I, g, c, beta, and t. And next equation is c equal f2 bracket I, g, c, beta, and t. Okay, the next step is f1 will equal with 0 and f2 will equal 0. At the equilibrium point can be rewritten as a follows. F1 equal y minus c minus I minus g equals 0 and f2 equal c minus c minus beta bracket y minus t bracket equal to 0. Suppose we want to obtain delta y per delta g and delta c per delta g. To do this, all other exogenous must be held constant. Thus, f1 will equal to 0 and f2 will equal to 0 should contain y, c, and g only. Then, totally differentiating f1 and f2 yield. Like this equation. After that, collecting the terms and dividing each term by this equation. The next step is converting into the metric form, and then we can obtain like this equation, equation 3. Since the metric at equation 3 is Jacobian, its elements are the same as those in the Jacobian determinant in equation 1. Also, since delta f1 per delta g equal minus 1 and delta f2 per delta g equals 0, then equation 3 can be written as 1 minus 1 minus b and 1 bracket delta y per delta g and delta c per delta g bracket equal 1 and 0. Then, using the Cramer's rule, we obtain that like this equation. And then, this means that an increase in the government purchase leads to an increase in equilibrium level of aggregate income and consumption.
Hello, my name is Lim Ding Yai, machine number 292024. Okay, let us look at the first question, where the question given the national income model y equal to c plus I plus g, c equal to c bracket yd, and t equal to t bracket y. And the question also asks to show that the two conditions of implicit function theorem are satisfied at the equilibrium points. To solve this problem, we must understand the given equation where the y equal to c plus I plus g and c equal to cyd, where the y is the y equal to yd minus t and t equal to t minus t bracket y. Okay, for this equation, we know that c bracket y is more than 0 and but less than 1. T bracket y is more than 0 but less than 1. After understanding this equation, the first step should we do is convert this function into equation where the f1 is equal to y minus c minus I minus g is equal to 0. F2 is equal to c minus c bracket yd equal 0. And f3 is equal to t minus t bracket y equal to 0. The function f1, f2, f3 have continuous partial derivative and this function are respect to the relevant variables. Thus, the first condition is satisfied. The next step is find the total differential. We use the three formulations such as the one df1 over dy times dy plus df1 over dc minus times dc plus df1 over dt and dt then times dt equal to 0, and also the other one such as f2 are same. Sorry, this is tf3. I mistake in this. Okay, tf3 and also the tf3. Okay, so we get the answer where df1 over dy is equal to 1, df2 over dc is equal to -1, df3 over d3 is equal to 0, and df2 over dy is equal to negative c bracket yd, and negative and df2 over dc is negative is 1. df3 over d3 is c bracket yd, and df3 over dy is equal to negative t over bracket yd, and sorry, this is df2. Okay, the df2 over dc is equal to 0, and also df3 over d3 is equal to 0. The next text is convert into the matrix from J x equal to B. So before we get the answer right, so we convert into the matrix forms like this, and we just times minus. Okay, so we get the final answer is negative less than 0. That means J is not equal to 0. So the second condition is satisfied because J is not equal to 0. So in conclusion, the two conditions of the implicit function theorem are satisfied at the equilibrium points. Thank you.
Good day everyone, my name is Angeline Ho and my matrix number is 293570. Now I'm going to proceed with question B. Using the implicit function rule, derive the expression for partial y with respect to g, partial c with respect to g, and partial t with respect to g, and show the algebraic sign for each partial derivative. Suppose we want to obtain partial of y with respect to g, partial of c with respect to g, and partial of t with respect to g. To do this, all other exogenous variables must be held constant. Thus, the equation for f1, f2, and f3 should be equal to 0 and should contain y, c, t, and g only. Then, totally differentiating f1, f2, and f3 equation. First, let us look at the equation for f1. To totally differentiate the equations, we need to differentiate each term with respect to the variables y, c, t, and g. The same goes to the second equation for f2 and the third equation, f3. Now we can divide each term by derivative of g. Now we will differentiate each equation with respect to g. Let's look at equation 1 f1. Same goes to the second equation for f2 and the third equation for f3. Just divide each term by derivative of g for the equations. Moving on to the next step is converting into the matrix form. To convert the equations f1, f2, and f3 into Jacobian matrix form, we can write them as a system of equations. Let's define the variables and constant as follows. Where A is the Jacobian matrix, X is the variable vector, and B is the constant vector. On the right hand side, we can see the total differentials equation that is in matrix form. For example, for equation f1, differentiating f1 with respect to y gives 1. Differentiating f1 with respect to c gives negative 1. Differentiating f1 with t gives 0. The rest of the matrix equation we can refer to part A, in which we have done just now. Moving on is to use Cramer's rule. To apply Cramer's rule, we need to find the determinant of the Jacobian matrix J. We can refer to equation A for the determinant of the Jacobian matrix. Next, we are gonna replace each column of the Jacobian matrix with the column vector on the right hand side of the equation. So to compute the determinant, remember, we just take the top left entry, multiply it by the bottom right entry, and we'll put a minus in between. And we take the bottom left entry and multiply that by the top right entry, and we get 1 plus 0 plus 0 equal to 1. So that simply would be the Jacobian of that transformation. All you're doing is finding a bunch of partial derivatives and then multiplying and subtracting.